What if a traveler from another star system drifted through our solar system and we almost missed it? Out there, beyond the planets, beyond the sun's fading influence, space is not empty. It is vast, ancient, and constantly moving. Stars are born, planets collide, systems tear themselves apart. And sometimes the debris doesn't stay where it was created. Sometimes it wanders. For billions of years, our solar system has been quietly orbiting the center of the Milky Way, unaware of the countless objects drifting between the stars, rogue fragments, interstellar debris, travelers with no home. We always assumed they existed. We just never thought we'd see one. It wasn't supposed to be here. It didn't belong to our sun, and it was already on its way out. Astronomers noticed it, almost by accident, a faint speck of light moving against the background of distant stars. At first, it didn't seem important. Another small body, another routine detection, but as the data came in, the numbers stopped making sense. Its path was wrong, its speed was wrong, and its behavior was unsettling. This object showed no glowing tail, even as it passed close to the sun. It reflected light in extreme rhythmic flashes, suggesting a shape unlike anything seen before. And most puzzling of all, it began to accelerate, slightly but measurably, as if something invisible was pushing it. No engine. No plume, no obvious cause. And yet, it was speeding up. Scientists gave it a name from the Hawaiian language, Oumuamua, a messenger from afar, arriving first. At the time, no one knew how fitting that name would be, because this was not just another asteroid. It was not a normal comet, and it was not from here. For a brief moment in cosmic time, something older than our civilization, older than our species, crossed the stage of our solar system, and before we could fully understand it, it was gone fading into the dark, back toward interstellar space. What was it really? Why did it behave so strangely? And how much do we truly know, and how much are we guessing? In this video, we're going to separate confirmed facts from speculation, measured data from wild headlines, what scientists know for sure, and what remains a mystery. Have you ever wondered what an object from another star system would look like? Let us know in the comments. Because the story of Oumuamua isn't about aliens or hype, it's about how strange the universe can be, and how easily something extraordinary can slip past us, unnoticed. Discovery. On October 19, 2017, at an observatory on Haleakala in Hawaii, an automated telescope called Pan-STARRS-1 detected a faint moving point of light. Pan-STARRS was designed to scan the sky every night, looking for near-Earth asteroids that might pose a threat to our planet. What it found that night initially appeared routine, a small object moving against the background stars, catalogued like thousands before it. In the first hours after discovery, astronomers assumed the object was a typical asteroid from our own solar system. That assumption didn't last long. As follow-up observations refined its orbit, something strange emerged. The object was moving too fast. Its path around the sun was not a closed loop like planets or asteroids follow. Instead, its trajectory was open, steep, and fleeting, suggesting it had entered the solar system only once and would never return. When scientists calculated its orbit precisely, the conclusion became unavoidable. This object was traveling on a hyperbolic trajectory, meaning it was not gravitationally bound to the sun. It had come from interstellar space. For the first time in history, astronomers had clear observational evidence of a visitor from another star system passing directly through our own. This was not a theory, it was a measurement. The object was given a name chosen by the local Hawaiian community, Oumuamua. In Hawaiian, the word roughly translates to a messenger from afar arriving first. The name reflects both its origin beyond our solar system and the cultural significance of the land and people near the telescope that discovered it. It was a reminder that even global science is rooted in specific places on Earth. Astronomers also gave it a new kind of official designation, One-Eye Oumuamua. The one meant it was the first of its kind. The I stood for interstellar, a category that had never been used before. Until that moment, no confirmed interstellar object had ever been observed in our solar system. This wasn't just a discovery, it was my first. Proof of interstellar origin. When astronomers talk about an object's origin, the most important clue is its orbit. Most objects in our solar system follow elliptical paths, meaning they are locked into repeated loops around the sun. Planets, asteroids, and even long-period comets remain gravitationally bound, no matter how stretched their orbits become. A hyperbolic orbit, however, is different. It is an open path, a one-time flyby. An object on such a trajectory enters a system, curves around its central star, and then escapes forever. Oumuamua's orbit was unmistakably hyperbolic. To understand why this matters, imagine throwing a stone straight up into the air. If you throw it gently, gravity pulls it back. If you throw it hard enough to reach escape velocity, it never returns. The same principle applies in space. The sun's gravity can capture objects only if they are moving slowly enough. Measurements showed that Oumuamua was traveling far too fast for the sun to trap it. Even before it encountered the sun's gravitational pull, its speed already exceeded the threshold needed to remain bound. As Oumuamua approached the inner solar system, its incoming velocity was measured at about 26 kilometers per second relative to the sun. That speed is not something solar system processes can easily produce. Objects formed around the sun tend to share its motion through the galaxy, but Oumuamua arrived from a completely different direction with a velocity that pointed clearly to an origin beyond our planetary neighborhood. In simple terms, it wasn't orbiting the sun, it was passing through. Some confusion arose online because hyperbolic orbits can occasionally be caused by close planetary encounters. In theory, a gravitational slingshot from a massive planet like Jupiter could eject an object onto a hyperbolic path. Astronomers tested this possibility carefully. The calculations showed that no known planet could have provided the required energy. Oumuamua's trajectory did not trace back to any interaction within the solar system. Because of this, the scientific consensus was immediate and remarkably unified. Research teams from NASA, the European Space Agency, the International Astronomical Union, and independent observatories around the world all reached the same conclusion. Oumuamua was not born here. It was the first confirmed interstellar object ever observed passing through our solar system, and that fact is not speculative. It is based on precise measurements, well-tested physics, and agreement across institutions. Size, shape, and the most extreme object ever seen. Because Oumuamua was small, fast, and already leaving the solar system when it was discovered, astronomers never had the chance to capture a direct image of its surface. Even the most powerful telescopes could only detect it as a single point of light. Everything we know about its shape and size comes indirectly from how that tiny point of light changed in brightness over time as the object rotated through space. These changes in brightness are recorded as what scientists call a light curve. As an object spins, different amounts of its surface reflect sunlight toward Earth. A roughly spherical body produces small, gentle variations. Oumuamua did the opposite. Its brightness changed dramatically, by a factor of about 10, in a regular pattern. This extreme variation immediately told astronomers that the object had an unusually elongated or flattened shape. From the light curve data, scientists estimated that Oumuamua was somewhere between about 100 and 400 meters in its longest dimension. That range depends on how reflective its surface was, which remains uncertain. What stood out was not its size alone, but its proportions. The brightness swings implied that one dimension was many times longer than the other, far more extreme than typical asteroids observed in our solar system. Two main models emerged to explain the data. One suggested a cigar-like shape, extremely long and narrow, perhaps 10 times longer than it was wide. The other proposed a pancake-like form, thin and wide, rotating in such a way that it produced the same brightness variations. Both shapes are unusual, and both fit the available observations. With no direct images, astronomers cannot definitively choose between them. The reason this uncertainty remains is simple. Oumuamua was discovered after it had already passed closest to the Sun and Earth. It was fading rapidly as it moved away, and there was only a short window to observe it before it became too faint to track. By the time scientists understood how extraordinary it was already slipping beyond our reach. What made this object truly unsettling to astronomers was that nothing in our solar system looks quite like it. Known asteroids and comets come in many shapes, but none show brightness variations this extreme combined with an interstellar trajectory. Oumuamua didn't just challenge expectations, it expanded them, hinting that other star systems may produce objects very different from the debris we are familiar with at home. A violent past. Most asteroids and small bodies in our solar system rotate in a fairly orderly way, spinning around a single axis like a top. Oumuamua did not. Observations of its light curve revealed that its rotation was chaotic, a complex, tumbling motion rather than a smooth spin, and it immediately suggested that something unusual had happened to the object in its past. By carefully analyzing the repeating patterns in its brightness, astronomers estimated that Oumuamua completed a full cycle of this tumbling motion roughly every 8 hours. The motion was not stable, and the brightness variations showed multiple overlapping periods. This complexity made it clear that the object was not in a calm, settled state. but instead rotating in a way that reflected past disturbances. In space, tumbling is often the result of violence. A significant collision with another object can knock a body out of stable rotation, leaving it spinning erratically for millions or even billions of years. In dense planetary systems, close gravitational encounters can have similar effects, especially during the chaotic early stages of planetary formation when objects are frequently scattered and ejected. For an interstellar object like Oumuamua, these processes likely occurred long before it ever reached our solar system. It may have been shaped, battered, and destabilized in another star system entirely, then flung into interstellar space during a gravitational upheaval. Once adrift between the stars, there would have been nothing to slow its rotation or restore order to its motion.